Assalamualaikum and good day to all. Next we'll continue with the second part of equilibrium. Okay, the last part of this course. So these are the learning objectives that each and everyone must able to do. You should be able to predict salt solubility based on the solubility rules. Okay, so what types of salt are soluble, what type of salt are insoluble. Secondly is constructing ice table to determine solubility of product constant value. Thirdly, solving problems on precipitate formation after mixing two solutions. Next is describing factors that will affect solubility of a salt. The fifth one is listing application of solubility equilibria, and lastly, memorizing selective precipitation of ions. So what is solubility? So solubility is a relative term used to describe how much of a particular substance dissolves in a certain amount of solvent at equilibrium. Okay, how much, like 3 grams of sodium chloride able to dissolve in 5 ml of water. Okay, so that's what it means. Substances that dissolve very well are said to be soluble, whereas those that does not dissolve well, we call them insoluble species. So how does the mechanism of dissolving a salt? So by now you should know what salt is. Okay, salt is an ionic compound that is comprised of metal cation bonded to a non-metal anion. For example, we have sodium chloride, NaCl. Okay, so this is Na plus with Cl minus. So this is a metal cation. Okay, this is a non-metal anion. So dissolving of a salt is an example of equilibrium. So what does it mean by this? Okay, so this salt, sodium and chloride, are initially attracted with each other. Okay, in the form of salt, means solid. Okay, and also they are attracted to water molecule. Okay, which act as solvent, for example. So therefore, when you place this salt inside water, okay, when you place the sodium salt inside water, okay, here, this attraction will loosen up because the cation and anion also attracted to the water molecule, which is the H plus as well as the OH minus. Okay, so Cl attracted to H plus and is plus attracted to OH minus. So therefore, this water molecule will start to pull out of this ion from the salt crystal. Okay, and this is the mechanism of salt dissolving in solvent. So what happened first? Okay, at first only dissociation of salt into ion. Okay, means the salt dissociate into ions. So let's say just now you have Na plus and Cl minus. Okay, so it will dissociate. Okay, initially the salt is NaCl, right? So it will dissociate into Na plus and Cl minus ion. Okay, However, soon the ion floating in the water begin to collide with this salt crystal, okay, and then pull back, okay, and then pull back into the salt, so they precipitate, okay. So this one can be pulled back here, okay, the free ion just now, okay, this free ion can be pulled back into the salt crystal, and these are called precipitation, okay. And until one point, the rate of dissociation will be equal to the rate of precipitation, okay, and this is the process we call saturated, means it has reached equilibrium. So that is why when you try to dissolve salt at home, okay, in water, and you try adding as much as possible salt inside the same amount of water, eventually the salt will not dissolve after it reach certain amount, okay, and that point we call saturation, saturated, okay, the solution becomes saturated, okay, it can no longer dissolve because the rate of dissociation and precipitation are equal. So in a saturated solution, there is no change in the amount of solid precipitate at the bottom of the beaker. Okay, means let's say you put 5 gram, okay, after it becomes when it reach saturated, okay, when it becomes saturated, let's say the amount no longer change, okay, let's say you put 5 gram of sodium chloride into 10 ml of water, okay, and then keep adding let's say 6 ml or 7 ml until at one point you notice it no longer dissolve. No longer dissolve means you notice solid at the bottom of the beaker, okay, even you add until 10 gram, okay, it can no longer dissolve, okay, so it has reached saturated solution, okay? No change in the amount of solid, okay. So concentration of the solution now becomes constant, okay, provided you add the salt at excess amount, it remains the same, okay, because the ion of the salt is no longer dissociated. So the rate at which the salt is dissolving in the solution equals the rate of precipitation. Okay, so this is equilibrium. Okay, next we move on to solubility rules. Okay, so if you look at the periodic table, the alkali metal, okay, if they become salt, they are very soluble. For example, sodium, okay, potassium, lithium, sodium. So these are very soluble despite whatever their anion is. Okay, so the alkali metal salts are very soluble. Okay. Next, ammonium salt are very soluble. So if you have any salt and it has ammonium as the cation, okay, it is very soluble, okay, despite of whatever anion with the ammonium salt, ammonium ion. So the next type of salt that is also soluble is nitrate ion. So whatever salt that have nitrate in it, for example, sodium nitrate, potassium nitrate, they are all very soluble. So besides nitrate, chlorate and acetate salts are also soluble. Okay, exception silver acetate. This type of salt is slightly soluble. Chloride salts are also soluble, except if the chloride are silver chloride, mercury chloride, and lead chloride. So besides that, they are soluble. Bromide and iodide also are soluble, again, except silver, mercury, and lead bromide or lead iodide. Okay, next we look at the insoluble salt. Okay, carbonate and phosphate are insoluble, except if the carbonate and phosphate cation are the alkali metals or ammonium. Okay, so if you have sodium carbonate or sodium phosphate, those are soluble. But if you have let's say lead carbonate or lead phosphate, okay, those are insoluble. And if you have ammonium carbonate or ammonium phosphate, those are soluble. Okay, but if you have copper carbonate or copper phosphate, those are insoluble. Okay, exception of the alkali earth metal are lithium. Lithium phosphate are insoluble. That are the exception. Okay, lithium phosphate. Next, hydroxide. Hydroxide are also insoluble. Again, exception is the alkali metal. And another exception is strontium and barium. Okay, so besides strontium and barium and also alkali metal, those type of hydroxide are insoluble. Okay, so if you have sodium hydroxide, it is insoluble. It is soluble. So if you have lead hydroxide, those are insoluble. But if you have strontium hydroxide and barium hydroxide, those are soluble. Sulfide. Sulfide, again, exception alkali and alkaline earth metal group 1 and group 2 of the periodic table, and also ammonium are insoluble. So if you have sodium sulfide and then group 2 barium sulfide, those are soluble. Okay, except the first and second group of in the periodic table and ammonium, they are insoluble. Okay, so this table is the sum up, okay, of the soluble compound and also insoluble compound. Okay. Okay, next we will continue with solubility product constant, KSP. So when a salt dissolves, it will ionize into ions. Okay, so look at this general equation for a salt. Okay, when it dissolves, it will ionize into cation and the anion that make up the salt. So when we write the expression, okay, for the dissociation of the salt, okay, so we use KSP. So S would refer to solubility product, okay, K constant. So note that we only use the ions concentration in bracket because in the expression we don't include solid or liquid. We only consider aqueous. So generally, solubility product means is the molar concentration of the ion, okay, raised to the power of stoichiometric power. Okay, for example, if we have salt here, magnesium fluoride, so MgF2. So when we write the dissociation of this solid, we get Mg2 plus and 2F minus, because it has to be stoichiometrically balanced in the product side as well as the reactant side. Okay, so when we write the expression, the concentration of the fluoride will be squared, okay, based on the stoichiometric value here, number 2. Okay, another example here, silver carbonate. Okay, so this is the dissociated ions. So when you write the expression of solubility product constant, okay, the coefficient will be written as the power. Okay, here for example. Okay, let us look at one example here, which is silver chloride salt. So it will dissociate into silver ion and chloride ion. Okay, so the KSP value, or the solubility product constant value for this salt, is 1.8 times 10 power negative 18. So where do we get this value? So this value is from experiment. So if you refer to any textbook, this value is all written at the back of the textbook. Okay, the product constant value. Okay, so again, we don't include solid because we are only dealing with the things that are soluble in aqueous form. Okay, so the KSP value can actually tell us whether that particular salt or compound is soluble or not. Okay, so normally if the KSP value is less than power of negative 5, the compound is considered as insoluble. And if the KSP value is in between 10 to the power of negative 2 to 10 to the power of negative 5, the compound is slightly soluble. Okay, and if the KSP value is larger than power of negative 10 power of negative 2, the compound is considered as soluble. Now let's look. So these are the KSP value for several type of solid or several type of salt. Okay, this value are found in the textbook. Okay, now how do we use KSP, or we use molar solubility to find KSP? Okay, first thing is writing balance equation. Okay, like the previous example. Okay, the product and the reactant has to be stoichiometrically balanced, and then we write the expression, okay, for KSP. Okay, next, calculate mole per liter, or the concentration of each ion represented in the KSP expression, and then we can calculate the value after substituting the concentration. Okay, one example here, silver iodide salt. So the solubility of silver iodide is 1.22 times 10 to the negative 8 molar. Note that because solubility is mentioned, so it's in molar unit. KSP, no unit. And in this question, you are asked to calculate the KSP value. Okay, so first things first, the first step is writing the balance equation. So this is the balance equation. Okay, silver iodide dissociate into silver ion and iodide ion. Okay, both balance. Okay, 1 1 1 1. So draw the ice table. So ice table, remember we don't include solid, we only consider aqueous form. So initially, no ions dissociate yet. Okay, so 0, 0. Okay, change will occur where this will be formed. So plus x. So at equilibrium, we have 0 plus x equivalent to x. 0 plus x equivalent to x. So substitute this into the KSP expression. Okay, so the KSP expression is concentration of silver times concentration of iodide. Okay, so here the coefficient is 1 because each is 1. So x times x given molar solubility here. So we substitute this concentration inside the expression here. So the KSP value is 1 times 1.49 times 1.49 times 10 power negative 16. Okay, don't be confused between molar solubility and solubility. Solubility amount in gram that dissolve. Molar solubility in number of mole. So actually molar solubility is molar. Okay, mole per liter. M, capitalized M. So how do we calculate molar solubility using KSP value? For example here, let us look at mercury sulfide. Okay, given the KSP value is 2 times 10 power negative 3. So to calculate molar solubility, the first step is to write the dissociation of the salt. Okay, so it will dissociate into mercury cation and sulfide anion. Okay, next is the ice table. So initially none of these ions present, so 0. And then change plus x, so equilibrium we have 0 plus x, 0 plus x, 0 plus x, and then we substitute this, okay, at equilibrium into the KSP expression. Okay, using the KSP expression, given the KSP value, we should be able to calculate the molar solubility, which is 4.47 times 10 power negative 27 molar. So there should be a unit here. Okay. Now, what if you were asked to calculate the molar solubility in a different unit, say gram per liter? Okay, use the value that you obtain based on molar. Okay, molar is also equivalent to mole per liter. Okay, and the unit, okay, requested is in gram per liter. So how to get this from this? So it means that we have to use the molar mass. So what is the unit of molar mass? Molar mass is in gram per mole. Okay, so means you have to times the molar mass so that you can cross this and this, leaving you gram per liter. So you should be able to solve this question if you were asked to find the the solubility in gram per liter. So this is the calculation. Okay, so the solubility in gram per liter would be 1.9 times 10 power negative 3 gram per liter. Okay, another calculation involved is if you were asked to calculate mass. Okay, so let us look at this example here. So given the molar solubility of solid nickel 2 carbonate is 3.7 times 10 power negative 4 mole per liter. So what mass of nickel carbonate needed to prepare 5
100 ml of a saturated solution. So how to solve this problem? Okay, so you were asked to calculate in terms of mass. So what can you obtain, how can you obtain mass using the information given to you? Okay, so you are given the molar stability, so it means it is in mole per liter, and the question is requiring in terms of mass, which is gram. So how to obtain this? So means molar mass is needed. Okay, so molar mass is needed, so you get gram per mole. Okay, so gram per mole, so you can cross mole and mole. Okay, now the final answer only 1 gram, which is mass. So you are given volume here, 500 ml, so therefore multiply with volume, so you can cross liter, so you will end up getting only mass, which is 0.022 gram. Now how do we use KSP to identify solubility of any salt? Okay, so generally we can say that salt with very small KSP value only sparingly soluble in water. Okay, but what if we have two salt and we are comparing the solubility between these two salt? Okay, so we can compare based on their KSP value. However, it only work if the two salt they are comparing have the same number of ion. If they don't have the same number of ion, then it's not comparable. Okay, for example, okay, copper iodide. Okay, so this is copper iodide. It has KSP value of 5 times 10 power negative 12. Okay, on the other hand, calcium sulfate have KSP value of 6.1 times 10 power negative 5. Okay, so KSP, based on these two KSP, okay, so the KSP for calcium sulfate here is larger, okay, larger than copper iodide. Okay, so we can say calcium sulfate is more soluble, okay, because this is copper 2 plus and iodide 2 minus, so this is calcium 2 plus, SO4 2 minus, so it's comparable. Okay, this is what I mean by when it has a different number of ion. For example here, copper sulfide with silver sulfide or bismuth sulfide. Okay, so we cannot compare these three because this is 1 to 1, this is 2 to 1, this is 2 to 3. Okay, so if you see the KSP value here, okay, so we can say this is the least soluble because very low KSP value. However, if we look at the experimental value, okay, the actual solubility of this bismuth sulfide salt, it is 1 times 10 power negative 15, which is the most soluble compared to the other two salt. So that's what I mean just now, it's not comparable if the number of ion are not the same. Okay, next we move on to see whether a precipitate will form if we mix two aqueous solution. Okay, for example, lead nitrate 0.024 molar, 15 ml, mixed with 30 ml of 0.03 molar potassium chromate. Now, will a precipitate form? Okay, the first thing that we do is write the balanced chemical reaction. So lead nitrate, okay, mixed with potassium chromate, so we end up getting lead chromate and potassium nitrate. So this is the solid form, this is remain as aqueous form. Now, our focus is this, okay? Because the question is asking, will a precipitate form? Okay, so what we do, okay, we write the dissociation of this salt here, okay, the formation of lead chromate. So it dissociates to form lead 2 plus and chromate 2 minus. Okay, now go back to the table, okay, in any textbook to find the solubility product constant of this salt here, lead chromate. So based on the table, the KSP value for lead chromate is 2 times 10 power of negative 16. Okay, so what is the rule of thumb here for a precipitate to form? Okay, if precipitate form, it means the solubility equilibrium has shifted backwards here. Okay, shifted backwards. Okay, so this will only happen if Q, okay, solubility QIP is larger than KSP value. Okay, now what do we do? Okay, we have this already. There's a reason why you are given the concentration here. Okay, so we use that to find QIP. Once we get the QIP, we compare with the KSP. Okay, so when we mix the two solutions, what happened to the concentration? The concentration will change. The lead aqueous solution will no longer be 0.024 molar. Okay, it's no longer this concentration. Chromate also no longer this concentration. So we need to find the new concentration after mixing. So after mixing, of course, the volume will change. Okay, so initially this is the volume of lead. Okay, and then this is the concentration. Okay, we divide with the new volume after addition, after mixing, and this would be the new concentration of lead. We do the same thing for chromate. Okay, find the new concentration for chromate. Okay, so this would be the new concentration of chromate. Now what do we do next? We substitute this concentration into the expression and we compare. Okay, whether the QIP is larger than KSP. So after substitution, the QIP value is 1.6 times 10 power negative 4. So we compare this value with the KSP just now. So this value is much larger compared to the KSP. Then we can conclude that a precipitate will form when the two solutions are mixed. So in the exam question, in the final exam, if you were asked whether mixing of these two solutions form precipitate, don't forget this last sentence. You need to include this. Okay, otherwise you will lose like 1 mark. Okay, because the question is asking whether a precipitate will form, so you need to answer that. Okay, other type of question is something like this. Okay, so the concentration of barium ion 2 plus in a solution is 0.01 molar. Given the KSP value for barium sulfate is 1.1 times 10 negative 10. Now look at the first question. What is the concentration of sulfate ion required to just begin precipitating barium sulfate? Question B. If the concentration of the sulfate reaches 0.015 molar, what concentration of barium ion will remain in solution? Okay, so this is another type of question that can be asked, okay, from you to solve. Okay, again, the principle is just the same. Okay, look at the question. Okay, it is asking you to find the concentration to just begin precipitating. Means at that point of concentration where the precipitate will form. So how do we do that? First of all, we need to write the dissociation of the salt, barium sulfate. Okay, so it dissociate to form barium 2 plus and sulfate 2 minus aqueous form. The next step is writing the KSP expression. Okay, so the KSP will be equivalent to the barium concentration multiply with the sulfate concentration, and we don't have the stoichiometric, so we don't have power of the concentration here. Okay, given the KSP value is 1.1 times 10 negative 10. Now the rule is precipitation or precipitate will form if the reaction quotient Q is larger than the solubility product constant K, KSP. Okay, so you are given the concentration of barium just now, right? Okay, question A is asking what is the concentration of sulfate in order for the precipitate of barium sulfate to form. Okay, so we rearrange because we have the KSP value, we have the barium 2 plus concentration. From here we can calculate sulfate. Okay, sulfate concentration. So this is the concentration in which barium sulfate still remain in aqueous. So to answer question A, sulfate concentration to begin precipitating is more than 1.1 times 10 power of negative 8 molar. Okay, because why? Q, okay, reaction quotient must be more than KSP in order for the precipitate will form. So if we substitute this back into the expression, we will end up getting the KSP value only. So the rule is it has to be more than KSP. So to answer that question, concentration of sulfate has to be more than 1.1 times 10 power negative 8 molar to begin precipitation. So next, how to answer question B. What is the concentration of barium plus ion so that this salt remain in solution form? Okay, so remain in solution form means again we use the KSP value. Okay, so now we have the sulfate concentration given in the question. Okay, so we are looking for the barium 2 plus now. So this is the concentration, the maximum concentration of barium 2 plus in order for this salt to remain in aqueous form. If the concentration of barium 2 plus exceed this value, means precipitate will form. Okay, question is asking what is the concentration of barium, okay, that in which barium 2 plus still remain as aqueous form, in solution form. Okay, next we move on to factors that will affect solubility of a salt. So there are three major factors which will affect the solubility of a salt. The first factor is presence of a common ion. I'm sure you are very familiar with common ion effect. Okay. Secondly is pH. So pH will also affect solubility of a salt. And thirdly is presence of a complexing agent. Okay, so I'm sure you are familiar also with the term complexing agent. Okay, you have studied this in analytical chemistry subject. So let us look at the first factor, which is common ion effect. So you know the rule is when there are common ion effect present, okay, solubility will decrease. Okay, Now, example here, try to dissolve magnesium fluoride in a solution that already have sodium fluoride. Now, what is the common ion in this two salt? Of course, the fluoride ion. Okay, so because the solution already have sodium fluoride, means less magnesium fluoride will dissolve. Okay. So this is the solubility of magnesium fluoride in sodium fluoride solution. So note that if the sodium fluoride solution concentration is low, okay, or means very dilute, then more of magnesium fluoride can dissolve. Okay, but if the concentration of sodium fluoride is high, then very small amount of magnesium fluoride can dissolve. So this is the common ion effect. Okay, next calculation problem. Okay, based on common ion effect. Now we have covered the concept. Now we look at the calculation part. So what is the molar solubility of silver bromide in pure water and its solubility in the presence of 0.001 molar sodium bromide? So we would expect the concentration between A and B would be different. Due to the common ion here, it will have less solubility. Okay, so let's do the calculation. So to answer question A, okay, very easy, okay, because we have covered this. Write the dissociation of the silver bromide salt. So it will dissociate into silver ion, aqueous, and bromide aqueous. And then ice table. Initially, none of this form yet. And then change plus x. So at equilibrium, 0 plus x equals x, 0 plus x equals x. So substitute this x into the KSP expression. Okay, here. Okay, given the KSP value of silver bromide, 7.7 times 10 power negative 3, we can solve for x. So x is the solubility of silver bromide, which is 8.8 times 10 power negative 7 molar. Okay, so we have a unit here. Okay, molar solubility. So what happened to the solubility of silver bromide when it is added added to a solution of 0.001 molar sodium bromide? Okay, so we write the dissociation of both first, sodium bromide and also silver bromide. Okay, so what is the common ion? Okay, common ion, of course, bromide. So it will be easier if we also draw ice table. Okay, let's see. We have ice table here. Okay, down below. Okay, initially, okay, no silver ion, but there is bromide present due to this sodium bromide solution. So it's 0.001. So C change x. This is also x. So at equilibrium, 0 plus x equals to x. This one, 0.001 plus x. So we substitute this into the KXP expression. Okay, now based on approximation, we can say 0.001 is very much larger compared to x. So we can assume that 0.001 plus x equals to 0.001. Otherwise, if we include this in the expression, you have to solve using the quadratic formula. Okay, so substitute this in the expression of KSP. Okay, we can solve x, which is 7.7 times 10 negative 10 molar. Now compare this value with the previous question, previous part A. So this would be lowered. Okay, this value is lower than the solubility in pure water. So we can prove that common ion effect will decrease the solubility of salt. Okay, try to do this exercise based on the example I have shown you. Okay, the approach is the same. Okay, only that in this practice exercise, you were asked to find mass of silver chloride that will dissolve. Okay, so to find this, you would need the information of the molar mass of silver chloride. Okay, so find the molar mass of silver chloride in order for you to find grams of the silver chloride that will dissolve, and this is the answer. Okay, for this practice exercise. Next, we look at the second factor, which is pH. So pH will affect solubility of salt compared to other factor. Okay, so the rule is, if a substance has a basic anion, it will be more soluble in acidic solution, and if the substance has acidic cation, it will be more soluble in basic solution. Okay, so you have memorized the different type of insoluble salt. Okay, so insoluble salt containing anion, for example, acetate, carbonate, hydroxide, phosphate, and sulfide, will dissolve in strong acid. Okay, so this is one example. Calcium carbonate, okay, it will dissolve in strong acid. Okay, so you will get calcium 2 plus aqueous water, liquid water, and carbonic ion aqueous form. So this figure shows the effect of pH to solubility of a salt. Okay, so this is magnesium hydroxide. Okay, salt. Okay, now what happened if droplets of strong acid added to this? Okay, to this test tube containing magnesium hydroxide salt. So what happened is the precipitate will dissolve. Okay, it will dissociate to form ion and will interact with the strong acid added. Okay, okay, how to solve this? Okay, consider the solution of any salt, okay, hydroxide salt, okay, in water. Okay, so it will dissociate to form aqueous cation and hydroxide anion. Okay, so go back to the Le Chatelier principle. Okay, now what would happen at equilibrium? So this is already at equilibrium. Okay, if we remove some of the hydroxide from the solution, so if we take this away, so it will disturb the equilibrium. So in this case, it will shift to, or it will move to the product side. So more hydroxide will form because this is already removed. Okay, so this will drive the solubility of this salt. Now how do we remove this? By the addition of strong acid just now. So when we add acid H plus, it will react with the anion. Okay. Now let us look at calculation involving pH. Okay. Calculate the concentration of lead 2 plus in each of the following solution and determine which pH is better to remove lead from drinking water. We don't want lead in our drinking water. Okay, because it's an example of heavy metal. Given the KSP value of lead hydroxide is 1.2 times 10 to the negative 15. So this lead hydroxide, would it be soluble in neutral pH or alkaline pH? Now how do we go about this question? Okay, first things first is writing the dissociation of the lead hydroxide salt. So it will dissociate to form lead 2 plus aqueous and hydroxide aqueous. Okay, so it will have coefficient of 2 because it has to be balanced in the product side as well as the reactant side. So next, what do we do? Okay, let us solve if it's in alkaline condition. So alkaline condition means the pH is 7, so pOH would also be 7. Okay. Now we anti-log pOH 7 to find the OH concentration. Remember in the expression, okay, of KSP, it should have lead concentration as well as the hydroxide. So we need to find the hydroxide concentration. So that can be calculated using the pH. Okay, so to find pOH, we minus from 14. Okay, so 14 minus pH, so we get pOH. So we anti-log 7 to find concentration of hydroxide. So the concentration of hydroxide will be 1 times 10 to the negative 7 molar. Substitute this in the expression. Given the KSP value, we can calculate the lead concentration. In this case, 0.12 molar. Now, what if it's in alkaline condition? Again, same approach. Find pOH. So 14 minus pH 13 is pOH will be 1. So we anti-log 1. We end up getting 0.1 molar. Substitute this into the KSP expression. Don't forget the coefficient. Okay, coefficient 2 to find lead concentration. In this case, 1.2 times 10 power of negative 13. So when you compare the lead concentration in neutral and alkaline, the lead concentration will be higher in neutral condition compared to alkaline. Okay, so means it will be safer if the drinking water is at higher pH. Okay, because the solubility of lead decreases, and nowadays in our home we have water filtration system, so the water will be filtered first before you drink, so it will filter off any solid salt. Okay, for example lead, which is harmful for us. Okay, but if the pH of the water itself is neutral, then the lead is in dissolved form in water, so it cannot be filtered out. Okay, and that will possess a health risk to us when we drink the water. So next, we look at barium hydroxide. So first, write the dissociation of barium hydroxide, which is barium 2 plus and hydroxide aqueous. Okay. So similar, if we add strong acid, so what will happen? The acid will react with the hydroxide. So this, based on Le Chatelier's principle, will disturb the equilibrium and it will make the barium hydroxide to shift towards to the product side to form more hydroxide. Okay. So in summary, how would it increase solubility of a sparingly soluble salt, for example calcium fluoride? Okay, so when we write the equilibrium of calcium fluoride dissociation, we get calcium 2 plus and fluoride. Okay, so to increase solubility of this, so that it will the equilibrium will move towards the product, we have to remove this fluoride. And how to remove this fluoride? We add strong acid. Okay, strong acid. So H plus will react with the F minus to form hydrofluoric weak acid. Okay, so it will drive the equilibrium to the right, means more of this calcium fluoride will dissolve. So when we add acid, pH will decrease, solubility will increase. Okay, next we look at the third factor, which is complexing agent. So presence of complexing agent can increase solubility of salt. Okay, so the first factor, which is common ion, will decrease solubility. The second factor, which is pH, will increase solubility. And this, the third factor, complexing agent, will increase solubility of salt. Okay, so what is complex ion? So complex ion is a charged species, and it consists of a metal ion which is surrounded by ligand. Now, what is ligand? So ligand is a Lewis base. Okay, it's a molecule or ion that has lone pair, and that lone pair can be donated to an empty orbital on the metal ion, okay, which is from the complex ion. Okay, and they will form a covalent bond. So I'm sure you're very familiar with this because you learned this in organic chemistry. Okay, so these are the common ligand. Okay, H2O, NH3, Cl minus, Cn minus, OH minus, SCN minus. These are all the common ligand. Okay, now the coordination number, okay, is the number of ligand, okay, number of this ligand here attached to the metal ion. Okay, so the most common coordination number 6, 4 and 2. So I don't have to elaborate more because you have studied this in organic chemistry. So these are the example of ligand complex ion. Okay, so we have COOH2 6 2 plus. Okay, we have NiNH3 6 2 plus. Okay, so this is coordination number of ligand. Okay, so let us look at one example, which is silver chloride salt. Okay, silver chloride salt, and we write the dissociation of the salt. So you will form silver plus aqueous as well as Cl minus aqueous. This should be aqueous. Okay, not solid. Then comes in the complexing agent. Okay, one example is ammonia just now. So ammonia will react with the cation. Okay, the metal. metal ion. Okay, so this is the metal ion. So silver plus. So it will form silver ammonium 2 plus. Okay, so this ammonia act as complexing agent. It complex the silver ion that dissociate from the silver chloride salt. So when this silver becomes complex, go back to the Le Chatelier principle. Okay, when this is complex with ammonia, we remove this. When this is removed, what happens to the equilibrium? It will be disturbed. So this will direct to more formation of silver. Okay, silver plus. So therefore, this will dissolve more because the equilibrium now shift to the right. So this is example of addition of complex ion to a salt. Okay, so this is silver chloride salt. Okay, you see it dissolves sparingly. Okay, so what happens when we add ammonia? It will complex with the silver and it will drive the reaction to the right, forming more silver ion because it complex with the addition of ammonia here. So therefore, more of the silver chloride salt will dissolve, and at one point it dissolves completely. Now, how do we apply solubility product expression? Okay, first we can predict formation of precipitate when two solutions are mixed based on the reaction quotient Q. Okay, so when Q is more than K, then precipitate will form. Okay, if Q is less than K, means no precipitate is formed. Okay, if Q equivalent with K, then both are at equilibrium. Okay, so we can say the solution is saturated. Now, what is the purpose of studying equilibria? Okay, solubility equilibria. So, without you noticing, whatever happen around us, okay, may involve solubility equilibria. Okay, for example, when you go into cave, okay, you see the stalagmite, the stalactite. Okay, so those are example of solubility equilibria, means precipitation of limestone, which is calcium carbonate. Okay, so calcium carbonate are insoluble. Okay, again, solubility equilibria means when you write the expression of calcium carbonate, you get calcium 2 plus CO3 2 minus. So the reaction is directed towards the reactant side. That's why you get this in solid or insoluble formation of stalactite and stalagmite. So this is in Turkey, deposition of calcium carbonate. Okay, very beautiful. Okay, so the white color here is the solid form of calcium carbonate. Okay, so means the equilibrium, okay, relies on the left, okay, which is the reactant side. Now another application related to solubility equilibria is kidney stone. I'm sure you're very familiar with kidney stone, and this will one of the health problem. Why kidney stone form? Now, if you in your diet you have intake of too much calcium, and too much of oxalate. For example, oxalate you get it from chocolate, you get it from spinach. Calcium you get it from dairy products. Okay, so if you take too much of this, okay, go back to the concept of equilibrium. Okay, when calcium oxalate or calcium phosphate dissociate, it will form calcium and phosphate or calcium and oxalate. Okay, so formation of kidney is when the equilibrium drive to the left. Okay, so when you have high concentration of calcium and phosphate or calcium and oxalate, okay, solid calcium phosphate or solid calcium oxalate will form. Okay, normally calcium that is not used by the bone and muscle will go to the kidney. Same goes to the waste product like oxalate. Okay, so when this oxalate, okay, when you have high intake of oxalate in your kidney as waste, as well as the excess amount of calcium in the kidney, they will form solid. Okay, solid kidney stone, and this can be removed through surgery or sound wave, things like that. So to avoid formation of kidney stone, then you have to decrease the intake of food containing high amount of calcium as well as oxalate. The next example is tooth decay. So we don't want tooth decay because it's very painful. Now our tooth enamel is made of calcium phosphate, calcium hydroxyapatite. Okay. So if you eat food, okay, and you don't brush your teeth, what happen is plaque will build up, and this plaque consists mostly of the bacteria from the food that you take, and this bacteria will consume the tooth enamel as its source of food. Okay, so because the hydroxide is used up, okay, by the bacteria, it will drive the equilibrium to the right. Okay, because this one has been used up by the bacteria, so the equilibrium shift to the right, so more of this will dissolve, and you don't want that to happen. Okay, so that is why we need to brush our teeth, and most of our toothpaste will have material or component like fluoride, right? And that will prevent the removal of hydroxide because you have fluoride. Okay, so you protect your tooth enamel. The next example is gout. Have you ever heard of gout? Okay, so this is due to the precipitation of sodium urate in joints, especially in legs. Okay, so this sodium urate, okay, if we write this KSP expression, we don't want the equilibrium to drive to the left. Okay, left means for similarly like kidney stone. Okay, so we want the equilibrium to drive to the product side. Okay, we don't want the solid formation of sodium urate. Okay, so to prevent this, again, food intake also. Okay, so those we have gout problem, we have to avoid product that will initiate the formation of this sodium urate. Okay, for example, soya products. Okay, or tauge. Okay, or seafood. Okay, so this is example of solubility equilibria in industry. Okay, example, production or synthesis of many inorganic compound involving precipitation reaction from their aqueous solution. Okay, so how to get solid from aqueous, then based on the mixing of aqueous solution, which must be reaction quotient more than the KSP value. And then how to separate metal from their ores. Okay, this will involve this solution. Again, we play around with the solubility equilibria. Okay, whether we want the equilibrium to shift to the right or to the left. Another example is qualitative analysis of identifying chemical species in solution involving characteristic precipitation in the solution, reaction of salt. Water treatment, okay, or purification involve precipitation of metal as insoluble in organic salt. For example, the previous question involving lead just now. Okay, so that's one example. Next is toxic lead, mercury, cadmium. Okay, remove as insoluble sulfide salt. Okay, so we get lead sulfide, mercury sulfide, and cadmium sulfide. So we can remove this through filtration. Okay, phosphate also can be removed as insoluble calcium salt. Okay, precipitation of gelatinous insoluble aluminum hydroxide. Okay, we remove suspended matter in water. Okay, so many process without you noticing is involving chemical equilibrium. Okay, this is one example of selective precipitation of ion. So let's say in one test tube here we have a mixture of ion. And how do we want to separate this ion? Okay, so we precipitate them out. Okay, so it will involve several precipitation process. Okay, for example, you want to get ion A. So you want it to precipitate out, you add the precipitating agent for that specific ion, and the rest will remain still in aqueous. And then if you want to remove the next ion, then we add another precipitating agent that will form solid with that particular ion, and the rest will remain as aqueous form. Okay, specifically, we have this mixture of cation. Okay, so these are group, okay, into 5 group, okay, based on their precipitation behavior. So we have group 1 here, group 2 here, group 3, 4, and 5. Now, how to collect group 1? Okay, so we add 6 molar of hydrochloric acid. After addition of hydrochloric acid, group 1 will precipitate. Okay, it will form solid, and the rest will still remain as aqueous form. And to separate, we centrifuge. Okay, centrifuge, then we can collect group 1. Now, how to collect group 2? Okay, to collect group 2, these ions here, we acidify this aqueous solution to very acidic pH 0.5, followed by the addition of hydrogen sulfide. Then it will precipitate out, okay, the group 2 cation. Okay, the rest will still remain as solution form. Okay, to separate, we centrifuge. Then how to obtain group 3? We add ammonia, ammonium buffer solution at pH 8. It will precipitate out group 3, and the rest still remain in solution form. And next, to precipitate out group 4, we add ammonium hydrogen phosphate, and what remain behind is group 5. So that is how we separate mixture of ions. Okay, so this is the sum up of that previous figure just now. Okay, again, summary of the figure, the previous figure. Okay, group 1, group 2, group 3, group 4, and group 5. And these are the selective precipitating agent for different group. And this is the compound we can obtain from the precipitation process, and the value of KSP for every salt form. So another example of precipitation is separation of metal ion, okay, based on their solubility. For example, we have silver chloride, silver bromide, and silver iodide salt. And how do we separate this? Because initially they are all homogeneous in the presence of ammonia, for example. So how to separate? Okay, we compare their KSP value. Okay, so silver chloride will have the smallest KSP value, so it's the most soluble. So the most soluble will easily precipitate out. So we precipitate out silver chloride, followed by next addition of precipitating agent to precipitate out silver bromide. Okay, and lastly, what remain behind is silver iodide. Okay, another example is you have mixture of solution that have silver, lead, and copper ions. How to separate these three? Okay, so what do we need to do first? Find the precipitating reagent. Okay, for one or more of the cation, and the rest will remain in solution, like the previous example in the test tube just now. Okay. Secondly, we compare the KSP value like the silver chloride, iodide, and bromide. Okay. So, based on the three ions just now, silver, lead, and copper, silver and lead, okay, will form insoluble chloride. Okay, so we will add hydrochloric acid, okay, because you want the Cl. So Cl will react with the silver to form silver chloride, and Cl will also react with lead to form lead chloride. Okay, and what will still remain in solution is copper. Okay, so that is done. We have copper. Now how to separate that solid silver and lead chloride? We compare the KSP value like we did for silver chloride, silver bromide, and silver iodide. So now we compare silver chloride and lead chloride. So the KSP value for lead chloride is 1.7 times 10 negative 5. The KSP value for silver chloride is 1.8 times 10 negative 10. So from this KSP value, the lead chloride is more soluble. When it is more soluble, means we add hot water, the lead chloride will dissolve and silver chloride will remain in solid form. So we can separate lead and silver. So this is practice exercise for you to try. Okay, solution containing chloride and chromate, and then solution of silver nitrate is added slowly. So which will precipitate first, silver chloride or silver chromate? Okay, so you compare the KSP like we did for silver chloride, silver bromide and silver iodide in the previous example. So the answer would be silver chloride due to the KSP value that is lower. Okay, 1.8 times 10 power negative 8. And we are done with this learning unit as well as this course. And I wish all of you good luck for your final exam.